quantum computing of all things at those times. So let's see. Let's dive right in. So what are we watching here? This is a robot doing a lot of the chores that many of us wish robots could be doing for us. But there is a catch. And the catch is that this robot is being teleoperated. Eric Berger, one of the students who built the robot, is sitting inside a harness and puppeteering every single motion the robot is making. But what it also shows is that the electrical, the mechanical are ready. What we're missing is the artificial intelligence. Now, I don't mean to say the artificial intelligence is just a small piece missing. There's a lot of pieces, and I think that's why it's so exciting right now to be working in artificial intelligence for robotics. And here's a list of many of the challenges that I think we need to make a lot of progress on before we can have these kinds of robots doing these things under their own control rather than teleoperated control. In today's lecture, I want to cover a few of them, the ones in the first column, but the other ones are just as important. It's just we only have so much time, so we're going to only cover the ones in the first column. First one is fast reinforcement learning. Just to make sure we're all on the same page, I'm actually curious, who here is working in reinforcement learning? A few of you, great. Who here has never heard of reinforcement learning? Oh, wow, great. So then this slide should go very quickly. We have an agent. The agent is supposed to make decisions based on the current observation. As a consequence of that decision, something changes in the world, and the process repeats. And the goal is for the agent to somehow maximize against some reward function. For example, for a self-driving car, reward could be very positive for reaching a destination, maybe medium positive as you're making progress towards your destination, and negative for an accident, and very negative for a deadly accident or something like that. And so the goal would be for your agent to figure out, through its own trial and error, to maximize expected reward over time. What are the new challenges compared to supervised learning? In supervised learning, whenever an action has to be taken, there has been data showing for similar situations what the action is that should be taken. In reinforcement learning, the only supervision is in the reward function, which can often be very sparse. And so figuring out when you finally get a non-zero reward signal, what it can be attributed to is a big challenge. That's the credit assignment problem. Another big challenge is stability. When you have a feedback loop, you can destabilize the system. The way it typically would work is that you would make a small mistake. As a consequence, you're in less familiar territory. That results in you making a slightly bigger mistake, and this then spirals out of control. Third big challenge is exploration. If you want your agent to learn to do things it's never done before, well, it has to explore, try things. And trying new things can be dangerous and also difficult to decide what is worth trying, what is not worth trying, based on the experience you've had so far. Now, despite these challenges, there's actually been a lot of progress in reinforcement learning. For example, in learning to play video games. What we're watching here is, in this case, TRPO agent in action playing Atari games. And this is a neural net that has been trained from its own trial and error all the way from pixel values to deciding on what action to take. Another example, game of Go. Until recently, many people thought Go would not be solved for a very long time. But sure enough, in 2015, there was a Go player better than many of the best human players, and by now, significantly better than the best human players. And the recent Go player, AlphaGo Zero, is trained by just playing against itself. Pure reinforcement learning. Another example is Dota 2. It's one of the most popular video games. In this game, you play typically 5-on-5, so 5 humans against 5 humans, each human controlling a character. In the initial version we took on at OpenAI, it was 1-on-1. It was shown last year that the computer player can play better than the best human players. And then a couple weeks ago, on the 5-on-5 challenge, it was shown that the OpenAI bots were almost as good as the best human players, just not there yet, but better than many of the best human teams, even in 5-on-5. Here's another example, and here's the first one where we see the learning in action. What we're watching here is a neural net controlling this robot, choosing, based on the current situation, what motor commands to send to each of the motors. Initially, it's falling over, but it randomizes a little bit what it does, and sometimes it'll fall over later. When it falls over later, that's better. It'll favor that by running backpropagation, updating the weights in the neural network to make it more likely to fall over later again. And over time, it figures out what it takes to maximize reward, which is going as far as possible in this direction while making only a very small impact with the ground. Here, we swapped in a different robot. And that's the beauty of these approaches. The same algorithm can be used to train a neural network to control a two-legged robot, a four-legged robot, or train a neural network to play Atari games, and no new code has to be written. This is also in very sharp contrast with, for example, what traditionally would be done in robotic control. Traditionally, if you visit a legged locomotion lab, they would tell you about center of gravity, support triangles, static stability, dynamic stability, and all these considerations would have to come together to somehow result in designing a controller that can make the thing run. But with this approach, you just can have it learn on its own. And you can have a different objective. Here, the objective is get the head to standing head height, and it invents how to get up. If you wonder how long does it takes about 2 weeks in real-time training. So it's a little long, but it's not crazy long either. But it's definitely still on the longer side for practical experiments, because if you run it on a real robot, usually your first experiment will not succeed. Then you need to run it again, again, and again. So we definitely still want more data efficiency than what we have now, but it's getting decent. Here is an extension to train the same kind of system to do a wide range of skills. And this, in this case, the character shown on the left is motion capture data. Actually, the one on the right is the motion capture data, I believe. The one on the left is the learned controller in action. And the beauty of having a learned controller to control the characters is that now you can apply perturbation forces. You can assemble them together in a long-term behavior rather than having just a replay of some mocap motion. You can apply the same thing to animals. In this case, the lion, when you see the big red arrow, is being perturbed by a big force, and you see that it can dynamically adjust to keep running in the direction it's supposed to be running. It can be done with real robots. This is a PR2 robot living on the 7th floor in the building I'm in at Berkeley, and it's learning to stack the Lego block onto the target location, which is the bottom corner closest to it. You can do it with cars. What we're watching here is the learning in action for a small car learning to navigate hallways. So it gets negatively rewarded for collisions, gets positively rewarded for making forward progress, and over time, this takes about 5 hours, it figures out how to reliably navigate the hallways in Corey Hall in Berkeley. And this one is a video from a collaboration with NASA. What we're doing here is controlling the Super Bowl robot. This robot is meant for planetary exploration. You might wonder why a robot like this? Why not just a robot with wheels? Seems more intuitive. Well, if you want to get somewhere, the size of your wheels will constrain what obstacles you can scale. And so here you have a sphere. So essentially have as big a wheel as possible in every possible direction, all at the same time. Now controlling it is harder, but reinforcement learning, actually purely done in simulation, then deployed on the real robot, was able to learn to control the system. So if we look at these results, it's fair to conclude that reinforcement learning can achieve mastery on a wide range of skills. But how good is the learning itself? If we look at some statistics, a study from MIT here showing that humans after 15 minutes can do as well as the best reinforcement learning algorithms can do after 115 hours. So there's many orders of magnitude of difference in how fast humans learn versus how fast our best reinforcement learning algorithms can learn. So the question is, how can we bridge this gap? Can we get closer to the 15 minutes of learning instead of 115 hours to get to that level of performance? Well, a starting point for our work here, and also a lot of related work, is that if you look at the state-of-the-art algorithms in reinforcement learning, whether it's TRPO, A3C, DQN, Rainbow, and so forth, they all are fully general. And there's something nice about the generality. No matter what problem you present to them, they can solve them. But if you think about what reinforcement learning really is, what needs to happen is you're in a new environment. You need to figure out what that environment is, how it functions, and then optimize your behavior against that environment. And so from an information theoretic point of view, what you need to figure out is, how does this world work? And what these algorithms do, they have zero prior about how the world works that they're going to be placed in, and so they're going to need to collect a lot of data to figure it out. By contrast, the environments we see in the real world are only a tiny, tiny subset of the environments we could encounter in our mathematical definitions of possible environments. And so maybe if we take advantage of that, learning can go a lot more quickly. So the question is, can we develop faster algorithms that take advantage of this observation? Reinforcement learning consists of an agent and an environment. If we look under the hood, there's a policy or a queue function. On this slide, it's a policy that interacts with the world. And then a reinforcement learning algorithm now looks at those interactions and based on the interactions, updates the policy. In environment A, it'll learn a policy for environment A. Algorithm can stay the same for environment B, learn a policy for environment B, and so forth. But if we look at this in action, even though we've done many decades of reinforcement learning research, it's nice that the algorithm can be reused, but the learning remains very, very slow compared to human learning. So the question is, maybe as human designers, we're not good enough at designing these algorithms. Right now, we're just learning the policy, we're designing the algorithm. Maybe if we were to also learn the algorithm in some way, we can do a lot better. Now, why might you have hope that we can learn the algorithm? The intuition remains that ultimately reinforcement learning needs to figure out what is the environment that you're in, and if you have a strong prior over what that environment is or could be, then you might learn more quickly. So the way we could hope for having a faster agent is by having a set of prior environments with which the agent can collect experience. And those environments should be representative of future environments. For example, if you want to learn to play video games in the future, maybe the prior environments are all video games. If you want to learn to have a robot control something, maybe manipulate some objects, and all the prior environments should be manipulating objects. If you do that, then you could hope for some meta-algorithm. A meta-learning algorithm is one that learns a learning algorithm to extract from interactions with this environment effectively a strong prior on which it can act to, in the future, learn a lot more quickly when faced with new environments. So how do we formalize this? One way to formalize this is as follows. What we're interested in this case, is an agent. And the agent is parameterized by some parameter vector theta. And for now, it doesn't really matter what the agent is, just that it's parameterized. In practice, it'll be some kind of neural network, but in the future, maybe it'll be something else, like just lines of code that are parameterized. This agent is optimized to maximize on expectation when dropped in a new environment and when getting to act for a certain number of trajectories tau, capital K trajectories tau, maximize expected reward. And so an agent like this, if let's say dropped in an environment for capital K equal 2 episodes, episode 1, episode 2, then gets dropped in a new environment for 2 episodes and repeats, such an agent, if doing well on this objective, will have to collect high reward in just 2 episodes in a new environment. So if we can find an agent that does well at this, then this agent likely will collect high reward in just 2 episodes, which is very different from the 115 hours of training that we saw before for learning to play one Atari game. To make this a little more formal, how we do the training, this expectation here gets replaced by an empirical expectation. This is very similar to what happens in supervised learning. In supervised learning, there's training data, testing data. Same thing will happen here. There are training environments, there are testing environments, and the hope is that if the agent is good at collecting high reward in a small number of episodes in training environments, it'll be good at collecting high reward in testing environments too, in just a small number of episodes. How to then represent the agent? Can be many choices. First choice we made is to pick a recurrent neural network. Why might that make sense? A recurrent neural network is a generic computation architecture. So it can represent anything, including whatever we might want to learn. Under the hood, the weights of the recurrent neural network that are learned during the meta-training will correspond to the prior over possible environments and the algorithm that makes the adjustments to whatever environment you're currently dropped into. The adjustments, while acting in a new environment, will be encoded in the activations, the hidden units. This problem itself is actually a reinforcement learning problem too. You're trying to find the recurrent neural network that maximizes reward when dropped in some environment. So we can bootstrap off of existing reinforcement learning algorithms. In our case, we used proximal policy optimization to optimize for this agent. Okay, now we need to start testing this. One way to test it is to pick a problem that is very well understood, because then we can compare with existing algorithms. So the first testing environment we picked was the multi-arm bandit problem. In a multi-arm bandit problem, you have multiple choices of which bandit to choose at the current time. Each bandit has a different probability of payoff, but you don't know ahead of time the probabilities of payoff for each bandit. So it's fundamentally a very simple reinforcement learning problem, but has all the key challenges of exploration and exploitation. For this kind of problem, asymptotically optimal algorithms exist. So we're going to compare how well does an agent perform that is learned with this approach relative to asymptotically optimal algorithms. Here's a table. Gittins indices are the best performing asymptotically optimal algorithm in these experiments. They're Bayes optimal. What we see is that learning an agent results in an agent that is about as good as Gittins indices. So that's a good sign. That means that we can actually learn something interesting here. We can learn from interaction with many bandit problems in the past how to quickly zone in on a solution on a new bandit problem. But this is a problem we already have solutions for. So you might wonder why train an agent for this. Here's a harder problem, maze navigation. This is the agent's view. The agent gets to just see first-person camera view. We get to see a map here of the maze, but the agent doesn't have access to the map. That's just for our viewing purposes to understand what's happening. Now, what the agent has to do is somehow find the target. By exploring this maze that it's dropped into, seeing where the target might be, then go to the target, and then it gets dropped again in the same maze. Hopefully it remembers something about the previous episode in that maze and can find a target more quickly. It takes in raw pixel values and gets to control by steering 2 degrees to the left, 2 degrees to the right, or keep going the current direction. If you randomly run around in a maze like this, this is what you get. Now, if you meta-train on many, many mazes, then deploy the recurrent neural net agent in a new maze it's never seen before, this is what you get. And this is kind of what you hope for. It efficiently navigates hallways to see if the target might be there. Once it sees the target, runs to it. When it gets dropped in the same maze again, it follows roughly shortest path to the target to get reward very quickly again. These are the learning curves. This is meta-training. So there's no differentiation here between train and test curves, it turns out. Because while we're meta-training, every time we drop our agent to collect more experience for the meta-training, we randomly generate a new maze. And since it's randomly generated new maze, it's like a testing maze. So these are training and testing curves for meta-training at the same time. But they're for different random seeds. And so we see that for about 2/3 of the random seeds, this works really, really well. 1/3, it doesn't work so well. What could be happening here? Well, in machine learning, things can go wrong typically either by underfitting or overfitting. What does overfitting mean? It means that you are in a current maze, you learn to solve it, but what you learn about solving the current maze does not generalize on how to explore new mazes in the future. So it's like you memorized what you need to do in the current maze, and then you can't do anything with it going forward. That's something you can control for pretty well. You can put in regularization, make the updates steps small enough that this wouldn't happen. The other problem that can happen is underfitting. This is kind of classical for reinforcement learning because we're relying on reinforcement learning to train this recurrent neural net agent. And underfitting means that your agent kind of wanders around in the maze, only very sparsely finds a destination, gets reward, and when it does finally get some reward, it doesn't know how to do credit assignment, and figure out what it was that it did right or wrong to find this reward that then can be reused in the future. And that's what's happening here. So the 1/3 of the learning curves where it's not learning, it's just not getting enough signal and not able to get off the ground at all. So we looked at some other architectures that might be better at propagating signal. The first one is called Simple Neural Attentive Meta-Learner. Remember, our current agent that I showed so far is a recurrent neural net agent, at least LSTM network. So it's decent at retaining signal over long horizons, but it still loses signal if it's a very long horizon. This is maze navigation. This is a very long horizon compared to most problems, so very hard to keep signal. So instead, we investigated what we can do with a dilated temporal convolution, very similar to WaveNet architecture. But the issue with that is that you lose detail. So we combined the dilated temporal convolution with the attention is all you need architecture from last August to still be able to get detail from the past. Once we do that, we get something that we call snail, and actually works really well. Here's the bandit problem. It actually does better and can solve longer horizon bandit problems than the recurrent neural net can solve. And for the mazes, it can solve much bigger mazes. So here's a much bigger maze, and we see that our agent reliably explores this maze. You might wonder, why doesn't it go here? Remember, it doesn't have the map of the maze. It gets dropped in a maze, doesn't know the map, doesn't know where to go first. Sometimes it'll be lucky and go first in the right direction. But this time, it's not lucky. It didn't go in the right direction. It's actually more interesting to watch. Because if you watch it when it's unlucky, you can observe whether or not it wastes time redoing things it's done before. And what we see here, it does not waste any such time. It's making the right decisions and doing new things every time till it finds the goal. So that's one approach. Now I'm going to switch gears and switch to a completely different approach. And it's not one is better than the other. It's very different, and maybe the future will point out to us which one is actually better, but for now it's not clear. Model-agnostic meta-learning. In model-agnostic meta-learning, the starting observation is what's being done in computer vision. What's the standard practice there? Standard practice in computer vision is you train on ImageNet. Once you've trained on ImageNet, you then fine-tune on the actual task you care about. It actually works really well. But you might ask some questions about that. One question you could ask is, well, how does it generalize to behavior learning? Because ImageNet is just about images. And another question you could ask is, well, it seems like we're just kind of being lucky. You train on something, and then you train on something else, and it turns out that the first training helps the second training. But we didn't guarantee that in any way. We just tried it, it happens to work. Maybe in the future, for a future data set, it won't work. So how can we generalize this to behavior learning, and how can we make this more explicitly something that we can count on rather than hope that it'll just work out? So what we want is end-to-end learning of parameter vector theta that is good initialization for fine-tuning for many tasks in the future. Okay, so what does it mean to be doing fine-tuning? At test time, we'll be doing fine-tuning. It means that there's already a parameter vector theta that has been pre-trained. And then we get new data, or new experiences. And based on that new data, we make an update. And then we get a new parameter vector theta prime, and we hope that that will be a good parameter vector. The fine-tuned parameter vector theta prime. So how can we force this to be a good parameter vector? The setting is that there's going to be many, many tasks, and we want it to be the case that for a future task, we're guaranteed to do well after fine-tuning step. Well, what does it mean to be guaranteed to do well after fine-tuning step? Here's something, the way we can formulate this. We have many, many tasks indexed by I. And for every task, we use the same pre-trained parameter vector theta, look at the training data, do an update, and then check on the validation data whether we're doing well. If it's the case that for every one of those tasks I, starting from the same parameter vector theta, with one update on data from task I, we get good performance on the validation data for task I, then that means that was a good pre-trained parameter vector theta for this set of tasks. Now, again, just like in supervised learning, if we do well on training data, we hope we do well on test data. The correspondence here is that we hope that if we do well on training tasks, that we will do well in terms of fine-tuning quickly on test tasks in the future. So the role of data has been replaced by the role is taken up by tasks. And that's why we sum over tasks here, but the pre-trained parameter vector has to be shared across all tasks. Pictorially, what that means is that we have many tasks with different optimal parameter vectors, and we're hoping to find this parameter vector theta that's a pre-trained parameter vector that is good at solving, after one fine-tuning step, any one of the tasks. Turns out this works well on many of the problems I've already shown, and also some other control problems that all of the approaches I've shown so far work pretty well on. But maybe the more surprising thing here is that this is fully general. What do I mean with that? If you think about the recurrent neural net architecture, we know it's a fully general compute architecture. You can learn any learning algorithm, any prior, any learning algorithm. How about this approach, where you're forced to fine-tune with a gradient descent step? Can it learn any prior and any learning algorithm on top of that prior? And it turns out the answer is yes. And the reason the answer is yes is because at training time, you know that you're going to just get access to a gradient step. And the neural net that's being trained can then train itself such that a gradient step is the right thing for you to do at fine-tuning time. Simple example of this would be, you might say gradient descent seems very naive. A second-order method seems like it would be more efficient. Well, the neural network can condition itself such that the gradient coincides with a second-order step. And it can condition itself even better for doing more complicated things than just being a second-order step. And that's what's happening during the meta-training. So, what's our status? We have a maximally general approach, or set of approaches, where we train an agent that's represented as a wavenet plus attention or a recurrent neural net. We have the mammal approach, where we say we're going to do a policy gradient update at test time, and we need to be ready for that. What else can we do? Actually, there's something else we can do. When you look at machine learning, almost everything is driven by loss functions. And those loss functions are defined by hand. So an alternative third approach that might or might not ultimately prove better than any of the other two, and probably the ultimate result will be something that combines all of them, is to learn that loss function. Maybe if you learn the right loss function, when you get an experience and you do a gradient update against that learned loss function, you can very quickly learn to perform the new task. And we'll do that here through evolving a loss function. What does it look like pictorially? Or in an algorithm? Standard RL with policy gradients, collect rollouts, optimize against a surrogate loss, which is some loss function the designer defines as the right thing to optimize against, and then you repeat this process. Evolve policy gradients, we'll try to find the better surrogate loss through evolution. So we'll have an outer loop here. The lower box is standard policy gradient, and you could run this by defining, let's say, a proximal policy optimization loss function, which is some importance-weighted loss function. But instead of just using this, you can instead decide that you'll have a neural network that defines your loss function, and you have an evolutionary algorithm in the outer loop that optimizes the parameters of this neural network that defines the loss function. In our case, this is what the loss function looks like. At a high level, essentially what does it do? It looks at past experience, because that's what a loss function is supposed to do. Look at all the experience you've had so far. Based on that, define an objective, and then learning will happen by optimizing against that objective, and the objective is learned. We'll actually bootstrap off the PPO loss function. So initially when we train, it's a weighted sum between this and the PPO loss function, dominated by the PPO loss function to get a little bit of signal, get the agent to do some reasonable things initially. Then over time, the PPO loss decreases its weight, and it becomes more and more just this thing over here that's fully learned. And again, we'll have to do this on a wide range of tasks. If you do this on only one task, then it doesn't make sense. You want to learn a loss function you can reuse for new tasks in the future. We looked at random hopper, which is hopper with different physical parameters. We looked at random walker, which is walker with different physical parameters, and random reacher. What we see here is that compared to the best human-designed loss function we have to date, it actually learns more quickly. Now, of course, keep in mind that it's learning something that's a little bit task distribution specific, but it's able for a distribution over tasks like random hopper to learn a loss function that is better than the standard loss function. For narrow task distributions, we compared with MAML and RL squared, where they can do pretty well, and we see that indeed it can match up with that performance. You can also evolve the initialization, so then you're combining MAML with evolved loss functions, and that helps a bit, of course. And what we look at this experiment here is actual generalization. So what we said here is at training time, meta training time, all tasks involve running to the left. Then at test time, the goals will be on the right. So MAML RL squared will naturally learn a good locomotion gate for the and tend to send it off to this side over here. Whereas evolved policy gradients turns out to also learn a good locomotion gate, but keep a more open mind and explores much better in other directions and can learn to find these goals much more effectively. So what we see here is that essentially when you evolve the loss function, you learn something that's a little less specialized to the training set of tasks than if you train something like MAML or RL squared, which zone in much more precisely on the very specifics of your training distribution. There's a lot more work on meta-learning. This slide shows a bunch of work on meta-learning for optimization. It's where you learn to optimize more quickly than you could do with standard gradient descent, again, by exploiting the fact that you have a distribution over tasks. There's meta-learning for classification, a lot of references here. We actually use this at Gradescope, which is a company I founded a few years ago, where we essentially facilitate grading homework and exams. And whenever you have a new question on a homework or an exam, that new question cannot be just graded by having already trained a classifier in the past on this question. What you'd want is something that can quickly fine-tune to the new question how the person is grading it and then grade the rest of it. And so at this point, the person has to do about 10% of the grading work and 90% of the work can be done by the meta classifier that then understands how grading is supposed to proceed on these questions. So if you have any grading work in your future, try it out. You can try it out for free, and it'll save you a lot of time. Here are some examples of those questions. So these are the types of questions they can do really well at. Multiple choice, free-form multiple choice, where you don't need to fill in bubbles anymore. You can circle things, cross them out, and so forth. Fill in the blank type questions, and also things where you draw in some relatively structured pattern. You can also do meta-learning for generative models. What that means is that you, for example, in your training, meta-training distribution, have many handwritten digits and characters. Then at meta test time, somebody shows you a new character that you've never seen before, and then you immediately know what variations of that character might exist and still be the same character. And for RL, we'll see more in this talk. Okay, so that was reinforcement learning, kind of the biggest of the 6 things I wanted to cover. Let's switch gears to imitation learning. There's been a lot of success in robotics through imitation learning. Typically, the way this is done is by collecting a lot of demonstrations, running an imitation learning algorithm, and from that you get a policy that can do well in the environment that you're trained in. Tricky part is, if initially maybe you want to train for assembling chairs and next for assembling tables, you have to restart from scratch every single time. What we really want instead is something that can learn very quickly, maybe from just one demonstration. So what we'd want is something that takes in maybe many demonstrations in the past, from that understands what it means to be a demonstration of a task, such that in the future, one demonstration is enough for a new task to learn to do it quickly. So one demonstration for a new task is enough to do well. How can we formulate this as a learning problem? Because what we really want is somehow some kind of one-shot imitator setup. Well, there are 2 styles of approaches we could follow. We could go along the lines of the RL squared, learn a recurrent neural net that parses all past experience and based on that understands how to learn quickly. Or maybe MAML style, where we see many past things, from that get pre-trained and maybe then fine-tune on something new. Let's look at RL squared type approach. Here's how you can formulate this. What we have here is a demo of task I and a second demo of task I. And what it means to be a good one-shot imitator is to be able to do the right thing in this situation here based on having access to the full video of the other demonstration. Because if you can decide the right action in that new situation, that means that you have learned how to parse a video, make sense of it, such that in the current situation you know what to do, and then the next time, presumably you also know what to do, you'll again parse that video, decide what to do, and repeat over and over. And this you can actually formulate as an end-to-end learning problem. You have a neural net processing demo 1, you have a neural net processing the current frame in demo 2, and the requirement is that it predicts the correct motor torques at that time in demo 2. We tested this on block stacking. You might wonder why block stacking. Block stacking is a very long horizon task, and long horizon tasks tend to be more difficult for imitation learning than short horizon tasks. Also, with block stacking, you can define a task distribution relatively easily. A member of the task distribution is a certain configuration of blocks that you need to achieve, maybe A on B, C on D, E on F. So what we'll watch here on the left is the one demonstration is getting of a new task, a specific block stacking configuration that it needs to achieve. What we'll watch on the right is the execution of the recurrent neural net that parses the demonstration on the left, and based on that decides what to do. The recurrent neural net here looks at the current situation, has an attention network, currently is paying attention to block A mostly, probably because it knows from parsing this video that initially block A is the most important one to look at. And then here we'll see where it pays attention in the video, where what you'd hope for is that essentially it would pay attention to the beginning at first, but then also alternate between paying attention to the entire video to see which segment of the video matches the current situation, and then zone in on that current segment in the video to decide what to do, and then again pay attention to the entire video, decide where to look next, and repeat this process. And that's exactly what happens here. Pays attention to the first two blocks, pays attention to the beginning of the video. Then, after it's stacked A onto B, it checks the entire video, see what it needs to pay attention to next, realizes it's C, D, and E, starts paying attention to those, and this process repeats over and over. And it reliably stacks the blocks as demonstrated in just one demonstration. And in fact, the attention structure is quite similar to the attention is all you need structure that came out a year after this paper, where there's a lot of self-attention repeated over and over to have the blocks understand where they are relative to each other. How about the other approach, mammal? In mammal, remember that we're trying to pre-train, and then based on a little bit of training data, already get a good performance on holdout data. Our little bit of training data here will be one demonstration of the new task, and our holdout data will be the second demonstration of the new task. And so we'd hope that with one demonstration we have enough data to do an update to the neural network, to update the mapping from image to action, to be better at solving the current task. And the neural network here would predict based on the current observation, target action. At meta training time, we use these objects. At meta testing time, we'll use these objects. So at training time, we only have access to objects that we'll never see again in the future. These are a different set of objects. There are targets and holding objects. The task is to place onto the target. This is meta testing time. So these are objects it's never seen before. But it's seen before that objects tend to get placed onto other objects. Has learned from that to probably pay attention to what object goes onto what object, such that with one gradient update, it now has a policy that does the right thing in the new situation. Now, if you think about this problem here, we have a validation loss, training loss. This is what it is for behavioral cloning. What we need still is somebody to tally up the robot to do the right thing in the demonstration. But what we really want is learn from just a video. Can we switch to that? Well, let's take a look. Key idea here is going to be that we're going to use different losses between train and validation. What I mean with that is that at validation time, which we only need during meta training, because meta training is when we need the validation loss to train things up, we'll still need the teleop. But at testing time, meta testing time, we'll want to rely on only video, and we're going to use a different loss. So what we're going to do is we're going to say for this training loss, we're just going to use, let's say, next frame prediction, and hope that that's good enough to do a gradient update on such that we get a better policy out. So pictorially what it looks like is we have a network with two heads. At validation time, we use the head that looks at the actions, and this we only need to do at meta training time. For the training loss, we predict the next frame. And the hope is that by predicting next frame, do a gradient update through this part of the network, that gives enough update to make this side also work. And because it's trained such that one gradient update through here should make this side work, this can actually be expected to work out. Little caveat still that predicting next frame is not great for imitation learning because you learn to predict something that involves pixels and you pay attention to a lot of the wrong things that matter for action. And so that's hard to get to work. So in practice, we do something a little different. We actually also learn a loss function. Just like in the evolved policy gradients, we learn the loss function, same thing here. Easiest way to think of this is think of it as like a GAN type training. We have a discriminator here that defines the loss function on next frame prediction. So rather than pixel level prediction, we do loss against this learn discriminator. Discriminator is learned such that a backpropagation pass through the discriminator, through the network, all the way here, results in good performance along this path here. Now we can do one-shot imitation from video. This is a demonstration, just person doing it, no need to teleop. We do backpropagation through the discriminator learned loss, through that video prediction branch of the network, and then now we use the policy branch of the network, and it does the right thing. Okay, in the about, I think, let's see, 15 minutes we have left. I want to give you a quick overview on a few other ideas. We're not going to be able to get into the same detail as we did for the first two, but just to give an idea of other things that I think are very promising and where some initial results already exist. First one is leveraging simulation. Why we do want simulation? A lot easier to work in than the real world for many reasons. So maybe you build a simulator that's realistic, but that's actually hard to do. So the challenge is, how do you have a simulator be useful if building a realistic simulator is really hard and really expensive? Well, some people look at domain adaptation, where you have matched simulator and real-world scenarios. That turns out to be pretty hard to get to work, but definitely very promising. What I think is really surprising is that you don't even need this. There's an approach called domain randomization, and the idea is very, very simple, yet very powerful. If you have enough random instantiation of your simulator, even if none of them are realistic, what you learn in those different instantiations, if you learn something that's valid across all of them, it might also just work in the real world, which will just appear as if it's just another random instantiation of a simulator. Some earlier work had done this for quadcopter flight, finding the longest open direction. Our work looked at doing this for precise localization of objects. And here's training error on real-world localization as a function of only simulated training samples, none of them looking realistic. It matters how much variation you introduce, so having a large texture library or randomly generated textures for every sample you generate helps a lot. Pre-training on ImageNet actually doesn't make much of a difference. That's a little surprising, that after just 8,000 samples, having pre-trained doesn't help you anymore compared to no pre-training. We also then applied this to grasping, where we said if you want to train a robot for grasping, very expensive, you need a lot of objects and so forth, can we just train it in simulation? We generated random objects, because getting realistic object 3D models and simulation of that is very hard. Generated random objects, trained on that, tested it in the real world, and here is this in action, where the robot that's never been trained in the real world is reliably picking up objects that are placed in front of it here on the table. And so the key idea here is in some sense a shift from thinking about network architecture and learning algorithms. It's more thinking about what are the invariants that you care about and randomize over everything else. Randomize over lighting, randomize over texture, randomize over viewpoints and so forth, such that whatever you train based on that captures the essence. You can actually generalize this to full hand manipulation. It's a more recent result from OpenAI, where the same idea is applied to in-hand manipulation. Very hard problem to simulate. So you have dynamics randomization here, and you train a neural network that works across many randomizations of the simulator, and then happens to also work in the real world. The goal is shown on the bottom right, and then it's trying to get it into that configuration. As far as I know, this is the most advanced in-hand manipulation skill that's been a robot been equipped with so far. All trained in simulation. Another problem I think that's very important is the distinction between how we're currently doing machine learning and how we'll probably need to do it in the future. Currently, machine learning tends to be something where you first run machine learning and then you deploy. But then all the learning happens ahead of time and the world continuously keeps changing. So the question is, how is that a good match with real world deployment? It's not. So really we want to keep learning. There's a lot of work on continual learning and some of it is listed here. What I think is different between what we can do now and in these older works is that we have much better frameworks for formulating this. Because thanks to the automatic differentiation frameworks like PyTorch, TensorFlow, and so forth, we can formulate continual learning as an end-to-end optimization problem. For example, want to train an agent to be good at dealing with non-stationary environments? Sure, just train it where it's faced with non-stationary environments and has to be such that it adapts well in that sequence of environments. And then at test time, it presumably also do well at adapting in that new non-stationary environment. What could be some sources of non-stationarity? In robotics, dynamics could change because robots could wear out, or you could have competitors who try to outperform you, and then you need to adapt to continue to be better. The competitor is what we looked at, so what we're looking at here is robo-sumo. You have to try to flip the other one over or get it off the tatami. And what we investigated is what happens if, in this case, we have the green robot be one that is really good in the first match against an opponent, whereas the red one has been trained to be really good at adapting to new opponents. And what we see is that initially the green one wins because it's good in its first matches, but the green one doesn't adapt very quickly. In fact, it adapts with regular reinforcement learning, which is very slow. Just 100 matches will not lead to a lot of adaptation. But the red one is trained to continuously adapt with this end-to-end objective, and as a consequence is able to beat the green one quite frequently towards the end. We then did a population study to see what happens if you have part of your population be part of the population is meta-trained to adapt quickly. These are the meta-update versions, orange and pink. The pinkish one here has an LSTM, so it can adapt even more quickly than the orange one, which has a multi-layer perceptron. And we play 100 matches between two opponents. Whoever wins most of the 100 matches gets to live on and reproduce. And what we see here is that LSTM plus meta updates very quickly starts dominating the population because it tends to win all the later matches enough to win the 100-game set. Another idea I want to highlight is how to maximize signal extracted. If you have seen some talks by Jan LeCun, you might have seen this cake before. He likes to use the cake to illustrate kind of how to split up deep learning approaches into different pieces. For example, there is reinforcement learning, which he calls the cherry on the cake. He says it's really important. Cake is not complete without a cherry, but it's only a tiny part of the cake. Supervised learning is the icing on the cake. Unsupervised learning is the whole foundation of the cake. And here, volume alludes to amount of signal in some sense. So Jan is saying that in reinforcement learning, there's not a lot of signal. We can't do a lot of learning. Unsupervised learning, there is so much data that we should be able to use. So there's more we can do there. Now, of course, in reinforcement learning, a lot of people have combined auxiliary losses with reinforcement learning to get more signal. Here are some examples. But what I want to do is kind of rephrase this problem a little bit. This is Jan's cake, and representing standard RL as the cherry on the cake. But if you look for cakes online, here's what you can also find. This cake has many more cherries. And so if we can now hopefully come up with an algorithm that matches this cake, then that would mean that that algorithm infuses a lot more signal into reinforcement learning. And we can do this with hindsight experience replay. This builds on some prior work, especially the universal value function approximators that I'll show in a moment. What's the key idea? The key idea here is that you want to get a reward signal from any experience you have, not just maybe very sparsely. So how to do this? You do it by assuming that whatever happened was your goal. Imagine you send a robot to get pizza for you, and the robot comes back with ice cream. You could say 0 reward, that's the wrong thing. Or you could say, if I just had asked you to get ice cream for me, you would have done the right thing. So in that context, you would have gotten non-zero reward, and now you can learn. So that's the idea here. How to formalize this? We'll need to learn universal Q functions rather than standard Q functions. So goal is part of the representation here, what goes in. Standard replay buffer is also augmented with the goal you had at the time. The experience replay standardly would look at this equation here, but that will typically have 0 reward. What we're going to do is change this in hindsight, change what the goal was. As a consequence, the reward can become non-zero because we pick a goal that we actually achieved, and we get non-zero signal to learn from. Why can we do this? Because Q-learning works off policy. Yes, we were not acting with that goal in mind, but Q-learning is fine off policy, so we can, after the fact, swap this in and do updates based on the hindsight experience. How well does this work? It actually works quite well. Here are some examples. Let's see. Oh, didn't play. Okay. There was a pushing task where we see that hindsight experience replay outperforms the same approaches that don't use hindsight experience replay. Same for sliding, and same for pick and place, and outperform quite drastically. Okay, last thing I want to touch on is learning representations for behavior. Learning representations is at the core of many deep learning efforts, but how can we do it specifically for behavior? I want to emphasize, though, that we've already kind of done some of this. All of the things we've covered here are learning representations for behavior. You learn something such that a future behavior can be acquired quickly. But here I want to look a little more under the hood at some other approaches. First one is causal infoGAN. What's the motivation here? Classical planning has many advantages, but the downside is that it's not grounded in the real world. So it's hard to apply in practice, because you have these predicates that you don't know how to tie into raw observations. Model-free reinforcement learning has no problem with taking in raw sensory values, but is very sample inefficient. Model-based RL is in principle sample efficient, but in practice doesn't achieve the best performance because the models are maybe not good enough and are not building the right abstractions. The real question is, can we do something that combines classical planning with ideas from model-based reinforcement learning to get the best of all worlds here? We can't get all of that yet, but here's a starting point. What we're training is a causal infoGAN. What that means is we have a state, a next state. The generator from that generates the observation and next observation. There's a discriminator checking if that's realistic. There's a mutual information term here, which ensures that the state abstractions that are learned are meaningful state abstractions. Once you set this up, and we're not going into a whole lot of detail here, you can actually get very meaningful representations learned. So we collected a bunch of data off rope, where we move the rope around, and we ask in the latent space to interpolate between this picture, and then we generate the observations corresponding to the latent space interpolation. This actually works quite well, which suggests that this representation might be usable to later do robotic manipulation of something like a rope. And that's the key idea, is we want to get abstract representations where we can directly interpolate and based on that make a plan. This is a comparison with standard infoGAN and DCGAN. The big difference is that they don't consider the temporal cohesion, and as a consequence, the interpolation doesn't make nearly as much sense. I'm going to skip over this. Here's another idea I want to highlight. Imagine you want to learn a representation for good planning. How do people often do planning? You have some state space in which you can simulate forward. There's actions coming in. You get a final state. You want to be close to the goal. Now, usually you get observations rather than states, so you'll have to deal with that. You have to encode this and encode this here. Then you have to check how good was my plan in achieving the goal. Then you can apply a gradient on that loss function and improve your plan. That would be, let's say, optimization-based control, any kind of nonlinear optimization, MPC-style control. We'll do exactly this, but how do we get a good latent space for this? Because we don't want to do this in raw pixel space. Well, one way to get a good representation for this is to say, okay, if this is what we're going to be doing, we're going to do optimization-based control on this learned latent space. We need the result of that optimization-based control to be something good. So we put a loss around this entire procedure, and we compare the optimized plan against the latent space model with a demonstration. Once we do that and optimize this all end-to-end, what we learn is a latent space encoding that is such that if we do optimization in that latent space, we get good controls out that match the demonstrations. Here are some examples of environment in which we looked at this, and here are the learning curves showing that if you structure your neural network this way, which in some sense is a special case of a recurrent neural network, a very special case of a recurrent neural network, that it does learn a lot more quickly than if you just use a standard recurrent neural network. So it's a very good prior for learning to plan. What it also shows is, in this graph, is that it actually learns to plan. So it was trained with only 40 steps in the optimization in the inner loop, but then reused with more steps. By reusing it with more steps, you're relying on the fact that indeed it is optimizing a plan in there and hasn't learned something else that's overfitting maybe to whatever data you provided. And indeed, we see that learning against 40 steps, you can do more planning steps, 60, 80, 100, and so forth, and get much higher performance. The last one I want to highlight is learning skill representations. So the idea here is that if you think about a lot of representation learning, it's about mapping raw sensory observations into a latent space. And here are some examples. And this is useful when you have pixel input or something like that that you can't directly work with for plan optimization. But there are other things you could learn in behavior space. Namely, what are meaningful trajectories? What are meaningful behaviors? For example, if currently we do exploration the standard way, we just randomize actions or randomize the weights, but that doesn't build on any prior experience. If we look at a problem like this, and has to always find the reward somewhere on the semicircle, but it doesn't know ahead of time where the reward is, only knows when it visits the reward is there, it should learn an exploratory behavior to always go visit the semicircle until it finds out where the reward is, and then zone in on that, keep going there. So that would mean that effectively this robot here should have a prior over behaviors, rather than just a prior over how observations should be mapped onto a latent space. Similarly here, if the task is always to push a block into the target, but you don't know which one, you have to experience it before you get the reward, then it's important that you learn a prior of moving two blocks and moving them onto the target and see what happens, compared to just random jittery actions and see what happens. It'll take forever in that way to explore this space. So what we'd want is some kind of latent variable that represents, or latent variable space that represents behaviors. One way to do it is to have a lot of tasks that are indexed by some discrete variable. From there, compute an embedding, and the policy takes in the embedding, and somehow the embedding should have high mutual information with trajectories. If that's the case, then you've learned a latent space that is good for exploration in the future to have meaningful trajectories you try out by sampling that latent variable z. So you can in the future explore by sampling z rather than random actions. You can train this another way. You can actually set this up without discrete indexing. You can end-to-end train this. So we want a latent variable z, or a space here such that if we sample z, then the policy acts based on that fixed latent input and current observation, and you get to do this, let's say, 10 or 20 times, and then you do a policy gradient update. The policy gradient update results in good behavior. If that's the case, then z is a good way to index into interesting behaviors for exploration. And so we're going to end-to-end optimize for finding a good representation here for z, which effectively means a good representation living in these neural net layers over here to take what is just a Gaussian distribution into different behaviors out there that are good for exploration. If you do this for this task family here, actually works very well. So below here are the exploratory behaviors, and on top are the learning curves showing that the end-to-end training for exploratory behaviors works much better than if you don't really have a prior over behaviors. So far, this requires tasks ahead of time. Can you do this fully unsupervised? Maybe not fully, but there's some good progress. You could do this by setting up the same structure. We have a latent variable going into the policy, and trajectories live here too. And then there's different approaches doing different auxiliary objectives between trajectories and the latent variable, based on trajectory and discrete, final state and latent variable, current state and latent variable, or full trajectory and latent variable. And here's an example of this in action, where we see here 4 choices of sampling of Z corresponding to 4 different behaviors. And this is learned unsupervised, showing that you can learn 4 distinctly different behaviors in an unsupervised way. So to kind of recap what we kind of looked at here today, I think it's a really exciting time to be working in AI for robotics. There's a lot of challenges for us to still resolve. We looked at the ones in the first column, but also many, many interesting challenges in the second column. And that's it for me. Thank you.
Thanks a lot, Peter. That was a really exciting talk. I'm sure there will be questions, and I hope nobody minds that we take some time for those before we go for lunch. Any questions for Peter?
Over there. Yeah, so there's a couple of questions embedded in there. So the last question was about, should the agent have a model of the world? And I think the answer is yes, the agent should have a model of the world. Now, it might have that model in different formats. So one way to have a model of the world is to have kind of a narrow model where the model is just encoded in your Q function or policy for the specific current world and the specific current task. And you essentially encoded your model of the world by encoding a optimal behavior, hopefully, against that. A more general model of the world would be a policy that has as input a goal and can then achieve any goal that's provided as an input in this world. An even more general model, but maybe harder to use, would be a simulator, an internal simulator of the world, but then you still have to figure out how to act in the world based on what you see in that simulator. So building the simulator is the model-based RL approach, which is listed here. A lot of good ideas are being worked on there. So far, it's been proven hard to get performance that's ultimately as good as what people achieve with model-free. in that the model-based approaches learn a lot more quickly, but then start asymptoting at a lower level typically than the model-free approaches. Now there's some work on hybrids and so forth to try to alleviate this, but the pure model-based approach tends to struggle to get to the same high level of performance ultimately. Another question that you had, and I think it's very, very intriguing and it ties into the evolved policy gradients from this part is the reward external or internal? So for people, maybe it's easy to argue the reward is internal because the reward comes from our brain. And let's say drug addicts can like short circuit the reward signal and get very high reward by just infusing drugs, but maybe that's not that useful, but it still gives instantaneous high reward. And so the question is, well, if we give our agents their own access to designing rewards, maybe they'll start doing the same thing. They'll just, you know, choose a reward that's always high. And so one beautiful thing about having the reward on the outside is that you still have control over what the agent tries to do. You still, as a designer, get to choose, I want this agent to do this, or I want it to do that. Whereas if you just let it choose, it's not clear what it's going to choose. Now, where I think things are really headed is actually a bit of a middle ground. Because if you look at the current learning algorithms, they learn pretty slowly. So in practice, what happens is you design a reward, learns very slowly. Then you say, I'm going to design a different reward, shape it more, like give it a lot more guidance, so every step along the way it knows whether it's on the right path or wrong path. Now you're going to put a lot of work into designing that reward, and maybe it'll learn a bit more quickly, but maybe it'll even learn the wrong thing because now your reward is very complicated to design. And I think big question is how to automate that process, how to go from getting to specify a very abstract reward, but the agent's still using something that is very frequently coming in and gives a lot of signal. And so the evolved policy gradients kind of go in that direction because the evolution process has an outer reward, and then the loss function that's learned is like having a more fine-tuned reward function that gives more feedback along the way. It happens to be in the form of a loss function rather than the reward function, but those are very, very related. And so you can probably reformulate that same optimization, putting learned reward in there instead of learned loss, and you'll get something fairly similar, I suspect. Here. Mm-hmm. Mm-hmm. Yeah, so we've done 2 experiments along those lines, not with the NASA robot, but with simulated robots, and two very different approaches, and both seem to do reasonably well. One approach is the same as the sumo wrestling setup, but at training time, instead of facing the system with a new opponent every time, we randomly perturb the dynamics of the system over time. And usually there's some kind of, we pick something that we say is the end state of the dynamics, and we fairly linearly interpolate from beginning to end. And so it gradually decays, and maybe it's a 4-legged robot and one leg stops working or something like that. And it can be trained for that pretty effectively. If you want to be really effective, we've had a model-based approach which will saturate performance a little sooner than model-free, so you won't get the same asymptotic performance, but is extremely data effective, where we do something that's very similar to what people do in language models. So when people train language models, they train a recurrent neural net to predict the next character. And when they get a new text, and they want to get a good likelihood score in the new text, they actually keep training it while they're evaluating on the new text. So they're fine-tuning while evaluating, because then you zone in on the current data you're supposed to be predicting. And so you can do the same thing for dynamics models. And we actually train it with MAML. So we end-to-end train it such that the dynamics model is good at adapting quickly to whatever changes are happening. Ignacy Clavera is the first author of that paper. I forgot the exact title. But that works quite well. Question, yeah. Mm-hmm. Mm-hmm. I got the perfect slide queued up for you. So, this is just one domain, of course, but this domain maybe I'm most excited about. I'll highlight some other domains too. But so I spent the last 10 years at Berkeley. Then I spent during that 2 years splitting my time between Berkeley and OpenAI. A year ago, me and a few others left OpenAI to start this new company because we saw a bigger and bigger gap between what people are doing with robots in the research labs and what's being done in practice. In practice, almost all the robots just do the same thing over and over, and that really limits the scope of what your robots can do. But with current advances in imitation learning, reinforcement learning, you should be able to equip robots with richer skills that are sensory-driven and more adaptive to whatever the situation is, and new tasks can be trained up more quickly and so forth. And so that's exactly why we started this company, that we think we can bridge this gap and bring things from the lab into real world. And, well, a very far-out application would be something like the video of the robot that does household chores. But I think that's really hard. And the reason that's really hard is because typically you still need a pretty large amount of data to learn a skill. And especially if it's a very general skill, like load any dishwasher in the world with any dishes, that's an extremely general skill, would take a very large amount of data. But that's what you would need to be reliable in many, many houses. So I think the initial applications will all be in manufacturing, warehousing, construction, farming, maybe hotels and so forth, where you have very large scale of things that are still semi-structured. So I expect that we'll go from current extremely structured environments are needed for automation to semi-structured environments allow for automation. And then maybe 5 years down the line, we can go to completely unstructured homes and so forth. And so examples listed here, things like, how do you pick, you have a bin with wires, how do you pick out one wire at a time, make sure you shake it loose if there's multiple coming out and so forth. How do you deal with non-rigid objects like carpets? Those are questions that are very hard to answer with traditional automation, but in principle should be learnable today. So that's one direction. I think in general, reinforcement learning is still difficult to apply, but if you can train it up ahead of time, so you don't rely on reinforcement learning to be on the spot acquiring a skill, but it's something where you have scale and you can train ahead of time and then deploy, it becomes feasible to have reinforcement learning solutions and if robots make decisions for certain situations. And of course, in supervised learning, there's many, many applications, and any kind of input-output prediction. I think, I'm assuming your question was mostly about reinforcement learning probably, or a little bit both. Yeah, so in supervised learning, there's applications these days in, let's see, marketing, Salesforce. Put supervised learning into predicting, you're a salesperson, you have 100 leads, you don't know which one is most promising, you only have time to follow up on 5 or 10 today, which one should you follow up on? It'll tell you based on historical data. Another example is predicting what you're going to reply in an email or what you're going to type next. Another one would be, let's see, in targeted advertising, it gets used a lot. What are some other examples? Visual inspection. I was at I think there's a couple of people here from RoboVision today. I was at a presentation yesterday. Yeah, some people here with the black and orange shirts. I was at the presentation yesterday, and they apply some of these ideas for essentially providing visual intelligence in all kinds of processes, where visual intelligence was the missing component, and then now you can provide visual intelligence, whether it's agricultural applications, sorting in a factory, and so forth. I see a lot of applications in China on face recognition to track everybody, where they go. The biggest companies, the biggest new startups in China are in that space. Face++ and SenseTime, they're only 4 years old and a little over $5 billion valuation right now. So growing very fast. And many police departments buy their AI to find out where people are and track down criminals. So yeah, there's a lot of applications right now. I would say pretty much anywhere where predicting something would help you, you can start applying AI to predict things for you. Yeah, so it's a good question. So one way to think of evolution strategies, it's like gradient descent, but it's gradient descent where you pick a random direction and you might take a step in that direction or not as a consequence. So in some sense, each step is less informative because you have a random direction to either go with or not go with. But it's been shown surprisingly effective for quite a wide range of problems. First of all, if you have a non-differentiable objective, you might just have to use it. You might have no choice. If your objective is differentiable, even then it's been shown quite effective, largely because it can be parallelized so well. So if what you care about is wall clock time, then running evolutionary strategies is extremely fast. And the key idea there is that, let's say you standardly run gradient descent. What would you do? You'd have a bunch of computers working in parallel, computing gradient updates, and somehow having to sync the result of their updates periodically. What does it mean to sync that? That means you have to send a parameter vector, which could be 1 billion parameters in a large neural network, which is a lot of data to send back and forth. If in evolutionary strategies, it turns out that all you need to know from the other computers is what random seed did they use to perturb their parameter vector, and did they, let's say, keep or not keep the change. And all you need to send is that one number, the random seed, and then you can locally regenerate what the change was. And so you have extreme compression in terms of what to send across. And so once communication between machines becomes your bottleneck in your optimization, your distributed optimization, all of a sudden you might benefit a lot from using evolutionary strategies. And so I think even though one gradient step in itself is rarely going to be as effective, it definitely has a huge advantage in terms of massive parallelization capabilities when communication becomes a bottleneck. And of course, anything that's not differentiable. It's not clear what to do. And then related to that, often gradients will attenuate over time. So let's say that you train a recurrent neural network for a language model. You want really long-term dependencies. It's hard to get that thing to propagate. Even with LSTMs or GRUs, signal will be lost along the way. If you use an evolutionary strategy, you don't have that problem. And so you might be able to model things that have much longer horizon dependencies. Same in reinforcement learning, have very long horizons. It can be difficult to do credit assignment and so forth. That's where an evolutionary strategy maybe can capture some things that a gradient approach would not capture. Question in the back. Mm-hmm. So looking at the kind of set of things that we're missing. So I think this is going to be one of the big pieces where a lot of progress has to be made in the next few years. Because key is going to be for this robot to adapt to new homes quickly. And to adapt to new homes quickly, you need exploration behavior that is more targeted than random actions or weight perturbations. And that's essentially what this is striving for. And so I think if we can make a lot of progress on this, we might get some very fast learning in completely new environments. And now, the way it, of course, would likely be phrased that you combine some of this with some of this over here. And in fact, one of the ways that we did the learning representations for behavior was already end-to-end learning with MAML actually for a latent space that is good to encode trajectories to sample in latent space to get new trajectories that are interesting for exploration. So I think that direction we'll need to see more progress, but we'll make a big step forward if we can make it work. Another one is this one here. Didn't touch on it much or at all, but long horizon reasoning is something where current robots or current reinforcement learning results are mostly short horizon results because the reward is such that you only need to propagate over 100 steps to get enough signal to learn. But household robots will need to think over much longer horizons, so we'll need better structures. And I don't know what will happen here, but likely something along the lines of new neural net architectures, maybe something like feudal networks, maybe building on option, critic, and so forth, but maybe yet something different, but something that has different temporal scales in the way it behaves, rather than just a single temporal scale. And then this part here, even though model-based, all the models we learned so far are never that precise, I think there will be ways to learn models that are at least good to learn from, even if you still need to fine-tune in the real world. And so I think those will need a lot of progress. Those three would maybe the three to focus on most if you want to get to a household robot right now. On the reinforcement learning side, on the imitation learning side, I think we're getting very close actually. If you look at some of the learning from video results, I think that's quite surprising in many ways that it's possible to just show a video of something new, it can pick up on it. Now the horizon in that learning from video was still pretty short. It was like a 2-second thing or a 1-second thing. Getting that over longer horizons is still a big challenge. And it was still a narrow distribution over tasks. It was always placing an object onto another object, which is very, very limited in expressiveness. Maybe we need larger data sets for that. Maybe a different approach, not so clear. Where I think most fundamentally we need different approaches is down here and up here. Those are the ones where we're clearly not doing it right yet in my mind, and we need something fundamentally better. And once we do that, then maybe things will really start working well. Yeah, so that's a very interesting question. How to use side information rather than just direct play experience to learn something new. There's a bit of work on that. Maybe best person for work to check would be Jacob Andreas. He is currently a PhD student at Berkeley, but will be professor at MIT soon. And so his work has looked at things like, if you have instructions, can you learn more quickly? That's still different from just a book, but instructions getting incorporated into reinforcement learning to learn more quickly, and actually ties a little bit into this thing here. And what his work does, it learns abstract representations where the agent starts thinking in terms of instructions that it might want to follow when trying something new. So it's seen instructions in the past, it's in a new environment, it then hallucinates a sequence of instructions, then tries to follow those instructions that it came up with itself, and that's the way it explores something new. It's not exactly the same, but I think it's some of the most closely related work. Another author is Karthik Narasimhan, and he's at, I think he's now professor at Princeton. And he's done some instruction following work too. But just taking side information like a book, learn from it. I haven't seen anybody do that successfully just yet, but it would be very interesting to try to succeed at. And there's some new DARPA programs that just got announced where they're specifically asking people to write research proposals on that topic. How to incorporate side information either in form of natural language or in the form of structured knowledge bases. How to bring that into all the deep learning machinery that can do many other things, but currently is not using any of that side information yet.
We can continue conversations over lunch because I think you'll be around for a bit, right? For
yep.
Lunch. So lunch is provided outside, generally sponsored by IMEC. So let's go there and let's thank Pieter again.